On this episode of Coding 101, we continue with our embedded processor build.
Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Coding 101 is provided by CacheFly at CacheFly.com.
This episode of Coding 101 is brought to you by Lynda.com. Invest in yourself for 2015. Lynda.com has thousands of courses to help you learn new tech, business, and creative skills. For a free 10-day trial, visit lynda.com/C101. That's LYNDA.com/C101. Welcome to Coding 101. It's the Twitch show where we let you into the wonderful world of the code monkey / code warrior. I'm Father Robert Balacer, the digital Jesuit, and joining me is once again our super special guest co-host, Mr. Lou Maresca. He's a senior developer for Microsoft. Lou, thank you again for coming back on Coding 101.
Hey, thanks for having me back.
We had some fun last week. We were talking with Mark Smith about embedded programming, specifically how to use something like an Arduino to take a real-world problem and solve it through the power of code. This week, we're going to go back into it. But before we do that, you've got some more interesting news about the Internet of Things. This time, it's privacy and security.
That's right. I wanted to kind of go over some of the items around, Internet of Things and privacy security, kind of what that means and why you should actually secure things. What you can do personally to actually secure your stuff. I mean, if you think about it, there was a quote from Clemens Vaster, who's a really big guy at Microsoft. He's a principal architect on the Microsoft Azure project for Internet of Things services. And he says the Internet of Things takes IT to heart of the company's core businesses into our homes and into the health industry. So quite literally to our hearts. And if you think about it, that's basically you're securing data that's coming from your body, right? Data from wearables tracking your body location, how many steps you take, your heart rate, your blood pressure, your GPS location, motion sensors, Bluetooth, Wi-Fi. And so if you think about it, if you're not securing that data successfully, if you're not securing your personal information successfully, they could leak out. And now with the more use of Internet of Things and wearables, it becomes even more important, right?
Yeah, Lou, it's interesting that you bring that up. We just covered a story on This Week in Enterprise Tech a few weeks back about some gas stations, about 5,000 of them that were using ATGs. Those are automatic tank gauges. And it allows them to check what the level of fuel is inside the storage tanks, the massive storage tanks underneath fueling stations. They found that 5,000 stations across the United States had put those ATGs onto the internet using a serial to IP device, and they hadn't secured anything with any password. So if you knew the IP address, you could get into the network, and that basically gave you root access. You could mess with the gauge, you could say it was full or was empty, or you could just take away control of the pumping network altogether from the station. And I think of those kinds of examples anytime I hear of someone saying, Internet of Things. It's like, whoa. Because there's the Internet of Things, and then there's the Internet of Things that probably shouldn't be on the internet. And
right.
The line between them becomes really fine. Essentially what it comes down to is, did your programmer consider what would happen if this was now open to the entire world?
Exactly right.
Yeah.
I think one of the problems too is people don't realize that, you're wearing this device and it's integrated now with your life. And normally people, they go to their computer, it's personal. Maybe they use their gaming device personal. They can kind of restrict how much they use it. But when you're wearing a device on you, you're not, it's now part of you, right? So now you have to make sure that you're being cognizant of the fact that you're streaming sometimes large amounts of data, especially about yourself, and it needs to be secured.
Let's talk a little bit about the approach that Microsoft is taking. And again, we all know that you work for Microsoft, so we're not trying to be a shill here, but you come with a very unique experience because Microsoft is trying to implement a philosophy for security on the Internet of Things run through Azure. It's a 7-step process.
That's right. Yeah, they call it the secure development lifecycle, and it's not only for Azure, it's for basically any type of data you store on it. Not just for IoT, but for any type of data. And really, what it is just a development process that developers should be following to basically helps you as a developer build more secure applications, as well as making sure that you have security and privacy around your data and that you're meeting compliancy requests, as well as it could actually help you reduce your costs based off of specific processes that we follow. Again, like you said, it's made up of 7 phases. One's what they call it response, release, verification, implementation, design, requirements, and training. And again, it includes training for developers and even program managers around basic concepts and building secure software, how to protect that data, and also responding to security and privacy incidents. So it also talks about that. And really, they built into their services a lot of layers, not only to help you transmit the data securely from your IoT devices, but also make sure once the data is out there on the cloud, they're securing it. And you know what? Not only Azure is doing it, Microsoft, as well as Amazon's doing that too. They also have ways tools to protect your data in transit, just like Microsoft Azure. We have REST services, but they also have ways to make sure that it's secured on their servers as well. They have what they call identity and access management to make sure that they control your access to your data. They use special things called security tokens or secure token service, which has built-in encryption to store your data. It has rotating keys. And also they have what they call Amazon Cognito for securing your mobile infrastructure, as well as your hardware security modules for tamper-resistant storage. So there's a lot of extra security that these services are doing, not only Azure, but Amazon and even Oracle services that are doing for IoT devices. And you want to make sure you're using these services. And if you decide to build your own, you have to be cognizant of all these things when you're building them.
All right. Lou, let's talk a little bit about what it means for a programmer who, as we spoke of in the last episode, might be leaning towards the Internet of Things as their next big project, and hopefully their next big meal ticket. If you are going to specialize in programming for devices or programming for embedded processors that will be part of the Internet of Things, what are some of the things that you need to be cognizant of? In other words, what are the things that I should have in the back of my mind as I'm creating the next interface for the device that's going to be worn around a wrist that will be reporting to my Facebook page, or I'm going to be making the next smoke alarm that's going to be alerting some big data cloud so that they know exactly what's going on in my house. What would you like to give to the next generation of IoT programmers?
There are some rules to follow, and there's a lot of articles out there. One thing I would suggest is make sure that you're not trying to collect personal data on the device. Let the user go to some service somewhere and enter that in, where they can secure over HTTPS or however those services secure it. But on the device themselves, you shouldn't really collect any personally identifiable information like their name and their email address, all that directly on the device. If you're doing that, then you risk yourself the fact that now you're giving them telemetry data about themselves, like their heart rate and blood pressure and all that stuff, but you're also potentially leaking personal data.
Nice, nice. Well, Lou, we're going to be having more Internet of Things as we go on. I'm sure this is going to be one of these topics that is going to become synonymous with programming, especially when we start talking about programming of embedded devices, which we'll be covering. Now, when we come back, we've got Mark Smith, Smitty, remember from DEF CON? He's going to be coming back to show you how to build that clock that we showed you last week. That's right, we're going to give you all the steps you need to take Arduino in its raw form, all the parts, all the soldering, all the little bits of programming that you're going to need to make it become that very cool analog clock watch thing, which, by the way, is not connected to the internet. But before we do that, let's go ahead and take a moment to thank the sponsor for this episode of Coding 101. Now, when you think of knowledge, when you think of learning, when you think of where you go on the internet to get new skills or to refresh your old ones, where do you go? Well, if you watch Twit, you know that you go to lynda.com. It's the one-stop shop for everything you need to know about everything on the internet. Now, what is lynda.com? Think of lynda.com as the way to get professionally made videos that look good, that sound good, that cover the topics you want to learn about. Now, it's already February, and we got to ask you, what are you waiting for? You made your 2015 New Year's resolutions to become a better person or to get more skills or to become more hireable or to just learn more. Why aren't you using lynda.com? They let you invest in yourself and learn something new with their free 10-day trial. Lynda.com is used by millions of people around the world and has over 3,000 courses on topics like web development, photography, visual design and business, as well as software training like Excel, WordPress, and Photoshop. All of their courses are taught by experts, and new courses are added each week. Do you want to improve your job skills to ask your boss for a raise? Or maybe you want to make yourself more marketable to find a new job? Are you looking for a new hobby, for maybe new financial goals, or perhaps you want to find a better work-life balance? Well, lynda.com can give you all of that because it enables you to change the way you work, the way you learn, the way you live. That's the power of lynda.com. Some of the courses that I recommend are Programming with iOS, Swift Essential Training, The Foundations of Programming, Programming for Kids, and Code Clinic. It's an innovative series where lynda.com issues a monthly code challenge and experts can share their solutions using a variety of different programming languages. We use lynda.com here in the Brick House because we're switching over to Adobe Premiere on the PC from Final Cut on the Mac. Well, our editors need a reference that they can go to if they get stuck, if they want to figure out how the functions translate from one to the other. And that's what lynda.com is great for, because they've got searchable transcripts, which means you can jump directly to the part of each lesson that deals with the question you have. No more watching hours and hours of video to find the one 10-second clip you need. You just jump right there. We want you to invest in yourself because we care about you. We want you to learn. And we want you to learn with lynda.com. Sign up for a free 10-day trial to lynda.com by visiting lynda.com/C101. With your membership, you'll get unlimited access to every course on lynda.com, including access on your iOS and Android devices, plus new courses as they're added each week. That's lynda.com/C101 to try it free for 10 days. Go ahead. I challenge you to learn something new. And we thank lynda.com for their support of Coding 101. Now, let's get straight into this video. Remember, you need to have watched last week's episode in order to understand, but without further ado, here's Smitty. I'm back here with my code warrior, Mark Smith. Smitty, again from DEF CON lore, if you know it. You're going to find him in the Hardware Hacking Village. Now, last week, Smitty, we left the folks with a basic introduction to what embedded processors look like, what the Arduino look like. We gave them links, so hopefully they bought the components that we see before us, and they've got them in their possession. Now, if they didn't want to build one of these clocks, they don't have to.
Nope.
But we're now going to give them a tutorial on how to start putting things together.
Correct.
All right. So could you explain to me the components we've got here on this tile right now?
So, sure. First, I wanted to go over the Arduino a little bit and what it has and what its inputs and outputs are and what we can do with them. You'll notice over here that there are some analog inputs that the Arduino has an analog to digital converter built into it, and so you can read analog voltages. We're not going to be using those today, but that's something that's available. Over here is a power section where you can get various different voltages and ground and other things if you need those for the rest of your circuit. Up at the top, you'll notice a whole bunch of just numbered inputs and outputs, and these are their digital inputs and outputs.
Let's take a step back there, because there are some people who wonder about the difference between analog and digital input. Okay. You know, really quickly, digital means on or off. It only has two positions. It has two states, whereas analog, you can have how many different values?
On the Arduino, well, analog in theory is an infinite number of values, right? But on the Arduino, it uses an 8-bit analog value, so between 0 and 255, 256 different values.
And of course, our audience knows how to do that because we went through the binary episodes in the first module of Coding 101. But why would I use digital versus analog or analog versus digital? Again, let's think back to what you gave us last week. You were talking about figuring out something that you wanted to solve, figuring out a problem that you wanted to come up with a solution for, figuring out something that you wanted done in your life.
Yeah.
When would I say that's going to need analog or that's going to need digital?
So it depends entirely on what you're trying to do, like you said. If you have a light switch on the wall, that's not a dimmer switch. It's either on or off. That is a digital output. So if you want one of those simple on or off light switches, that would be a digital output. Whereas if you want a dimmer switch where it allows you to turn it up a quarter of the way, half of the way, 3/4 of the way, or whatever, that would be more like an analog output.
Right.
And you would use what is called a PWM output, or a pulse width modulated. I'm not going to go into the details of what PWM is or how it works. Just know that that's how you get an analog output from a digital system.
Right. And actually, we'll be talking about that in know-how. This is a great time for some crossover because servos on modern quadcopters will all be digital, but they use PWM to approximate analog.
Correct.
It's like you said, analog is technically, it's infinite, but an approximation of analog is not.
Correct.
It'll be limited by how many values you can create with the PWM values you have.
Yes. So the Arduino is not actually capable of outputting an analog voltage, but it is capable of outputting a digital voltage and turning it off and on fast enough so that the average voltage is an analog value, and that's what pulse width modulation is doing.
Right.
You'll notice that some of the numbers have little dashes in front of them. They're actually tildes, but you just can't see it very well. Those tildes specify which ones of these outputs are capable of producing a PWM signal.
Oh, okay.
Okay, so the tildes are the ones that can produce a PWM signal. The ones without the tildes are just digital only. Over here, you also see a TX and an RX. Pin 0 and pin 1 are used for the serial output, or input and output. And we will be looking at that a little bit later with our project. So that's what's on the Arduino. And then there are various other connectors. There's a USB connector there that's used for programming it and or powering it. If you don't want to have it hooked up to USB, you can just power it through a normal 2.1 millimeter barrel plug, like all of your appliances come with these days. And then there are these random 6-pin headers that are used for if you brick the Arduino chip and you need to reprogram it from the ground up.
Right.
If the bootloader is broken, you need to be able to just completely grab it by the brainstem and have it do something completely new. That's where you program it. And then that one over there is used to program the serial converter.
You told them to buy this, so hopefully they have one of these, but you also told them to get this proto board.
Proto board. So the proto board is these are what are called shields. So Arduino has the concept of a shield. The layout of this board is very well defined. The spacing of these pins relative to these pins, how many there are, what signal is on each pin, all of that information, including all the way down to these mounting holes over here, is all very well defined by the Arduino community, by the folks that make the Arduino. And so it's very easy for someone to say, all right, well, I'm going to make another board that has these long pins on them that I can just put right on top of the Arduino, like so, plug it straight in, and now it looks like one unit. And the
and you can actually stack these. I've seen Arduino boards with like 5 different shields on top of them,
exactly,
ending with like an LCD display.
Yeah,
right.
Yeah. And so these are called shields, and they are a kind of a standardized way of making a component that will fit onto an Arduino. This particular shield is a proto shield, and so it's got a bunch of these sockets, these holes on top that we can push the wires into that I showed you last week. This particular shield is one that I got because it was cheap. I ended up doing some things that I didn't like, so this is actually not one that I would recommend. The one in the show notes that from last week is the one that I do recommend. It's from SolarBotics, and I'm quite happy with that one.
This doesn't fit exactly. There are some unused pins that you can tell at the bottom.
Yeah, there are a couple over there.
Exactly.
So this board was meant to fit on a newer Arduino. Some of the newer Arduinos added a couple of pins over there, and they actually added a couple of pins over here as well. So there are some differences, but
for our purposes, this is going to work.
This is going to work just fine. It means that I won't be able to use the buttons that are included on the board over here. I can't use those. I got to add my own buttons.
Right.
But we'll do that. And then the other thing that we added, or that we had you guys buy, is this, and it is not a shield. It is not specifically formatted to fit on an Arduino, but it is a real-time clock. It is a DS 3231 mumble chip. I don't remember the exact number.
Now, we do have to stop here because a real-time clock, RTC, you always see RTC if you're doing any sort of embedded program. In fact, any programming whatsoever, if you look far enough back in the library, there will be a reference to the real-time clock. Why is a real-time clock so important in programming?
So, anytime that you care about timing, and timing meaning how fast does something happen, or how slow does it happen, or when does it happen relative to something else, or in our case, what the literal time is, wall clock time, you need to have a precise clock. The Arduino itself has a clock that's built into it. It's that little metal canister right there. That is a 16 megahertz clock, and it's 16 megahertz-ish. It's not very precise.
It's quartz, right?
It's a quartz crystal.
They just figured out that when you compress it, it's going to vibrate a certain number of times per second, and that's what gives you your timing.
Exactly. But it's not very precise.
Right.
And so if you rely on that to count the time, it'll be slow or fast, or it'll change over time. They're not very well heat compensated. For a microprocessor that's just doing stuff, it doesn't really matter. But if you care about the timing, like in your case for the quadcopters, I need to be able to spin those fans at a very precise speed, right? And I need to be able to set that servo at a very precise value. Okay, in that case, a real-time clock really matters. In our case, we're trying to tell the time, and I want to know what time it is, and I don't want my clock to drift over time. And so I want a very precise clock.
The old schoolers among us will know this problem back early in the IBM PC days.
Oh, yeah.
When we didn't really use real-time clocks, it was just the speed of the CPU.
Processor.
You assumed it was going to be running at a certain speed.
4.77 megahertz.
So I used to have video games, way old school video games, that you would upgrade and suddenly everything's running double speed.
Yep.
And that's why you had that turbo button on the front of the case, because you're like, no, I got to slow this thing down.
It's not the turbo button, it's the
slow down
button.
Right.
Yes, exactly.
So, and once they realized, oh, there's going to be a lot of different applications. You're probably going to be using this over time, which means the hardware is going to improve. They needed a way to make sure that the timing would always be the same.
Yeah.
And that's why we started using an RTC.
By the way, I think you and I just dated ourselves.
I know we did.
We remember turbo buttons.
Turbo button.
And I was able to bring out the clock speed of the original PC.
I still have one of those. I love that, the little front panel. And I always felt like, okay, engage turbo. Ah!
Yeah.
Now, why is this time clock so precise versus just the crystal on the Arduino?
So the chip on here is very specifically designed to have a very precise clock on it. It is a primary design component. More importantly, this particular one is even temperature compensated.
Oh, wow.
So one of the problems with clocks is that as they get warm or cold, they will speed up or slow down, or the other way. I never remember which one's which, but the time changes. And so one thing you can do is you can compensate for the temperature and speed up or slow down your clock accordingly. Some of them are temperature controlled, where it will actually have a little heater element on there and make sure it stays at a current temperature, or some are compensated, where it doesn't actually change the temperature, but it will measure the temperature and then adjust the clock accordingly.
We've got the RTC. Can you show us how we put these together? So I need the shield on top of the Arduino, and then I have to somehow interface the real-time clock with the shield.
Yes. So the real-time clock uses a protocol called I2C, or IIC. I have no idea what it stands for.
I used to know that.
It's a proper noun now. It's I2C. It is a serial bus. You see over here where it says SCL and SDA. That stands for system clock, or I'm sorry, serial clock and serial data. Those are where the actual data is between the real-time clock and the Arduino. And then VCC is your power source, and ground is your negative power source. So those 4 pins are all you need to populate this real-time clock to be able to get the data into and out of it. And then we have similar pins over on the other side. This particular real-time clock module just has them on both sides for convenience. What we are going to do, there are 2 other pins on top here. The 32K is a very precise 32 kilohertz output that you can use to drive other counters and whatever else if you need a very precise clock. We're not going to be using that. And then the SQW, I'm not entirely sure what that is. I think that stands for square wave. I think that's a pulse per second.
Yes.
Again, we're not going to be using that. All we care about right now are the power and the serial clock and serial data pins. We're going to be using the I2C bus out of this. On the Arduino Uno, I2C is on pins A5 and A4. That's just one of the standards that Arduino created when they first developed this board, and that's kind of something that we have to stick with. However, be aware that newer versions of the Arduino, specifically the Arduino Leonardo, which is a similar form factor to this, put the I2C pins on a different pin. They put the I2C signals on a different pin. So if you are going to be using an Arduino Leonardo or one of the other Arduinos besides an Uno, make sure you know which pins your I2C are.
No matter what device you're using, you have to check the documentation.
Exactly.
Make sure that it's going to match up with the pins you think they are.
Exactly. If you look at the pins on the real-time clock there, I can actually put put the real-time clock into the Arduino directly like that.
And we're not using the 32K, and we're not using the square wave.
We're not using the 32K, we're not using the square wave, but if you put them in like that, that puts the serial clock and serial data in the correct pins, and then I just need to configure the Arduino to give a positive voltage on the VCC and a negative voltage on the ground. Or not a negative, but a 0 voltage on the ground.
But of course, we're not going to be plugging the RTC directly into the Arduino because we want to go through the proto board.
We want to go through the proto board.
Components.
We can add components. So we'll go ahead and add the proto board. Just gently squeeze it on, make sure all your pins are lined up. I've got a couple extra hanging over there just because the proto board is designed that way.
But if you buy the one in the link, you won't. It will line up perfectly.
It will line up perfectly. So we have to add that in, and again, we've got a couple of extra pins hanging off over here. And so we plug that into the breadboard, into the proto board, and we still have the little power light lit up. And I will show you once we get to the code how that works. And in fact, I think now's a perfect time to get to the code.
Let's go ahead and take a look at the code. Now, we do have to say, it's not going to be as simple as turning on your IDE because you've added a component. The RTC is something very specific that not every Arduino developer is going to be using, so we need a library.
A library.
And everyone who's watched Coding 101 knows what libraries are. Libraries are basically just code that someone else wrote that you can import and use.
Correct. So we're going to be loading, we're actually not going to be doing it on show because it's dependent on what operating system you're running and where you get the libraries and all that. But it is a very simple process. There are lots of tutorials on YouTube. And
yeah, you learn how to do it once and then that's it.
And that's it.
That's it.
So in this particular case, you could, in theory, write your own code that talks I2C to the real-time clock and talks the protocol that the real-time clock is expecting and calls the right functions and pulls out the right data and all that.
You could.
You could, or you could just import the library that the people who made this have already written, and then you just call rtc.get, and you get all the data.
And our audience knows well enough that, yeah, you just use the library.
You just use the library, exactly. So that's what I've done on my code here. I have included the DS1307 RTC. So the 1307 was the first, one of the more common real-time clock chips. There are several other chips that implement the same protocol, and so and this chip is one of them. So you just load the DS1307 RTC library. It depends on another library, nope, not wire, called Time, so we'll be using some of those functions as well.
Right.
And that's all linked to in the show notes. Links to these libraries and where to get them and how to get them installed.
And so a quick programmer's note, anyone who has watched, again, any of our modules has seen includes before. It works exactly the same way. What you're telling the developer environment to do here is to look for the library that's after the include statement, and it will allow you to use all the functions that were written inside that library.
Correct.
All right, now, so we've got a bunch of define statements. What's going on here?
There are several places where I want to know what pin I need to apply power to, all right? And I could write A3 in all of those places. I got a pin mode, which tells it whether this is going to be an input pin or an output pin. And then I have a digital write that is going to say what value do I want to write to this pin. And then in some other cases, when we get later, we'll be using pins a lot more often in the code. But I could write A3 in every single one of those places. But then if I ever decide to change it, let's say I want to port this code to work on a Leonardo where the pin is on a different pin, all right, I could go through all of my code and look for all of the places where I wrote A3 and hope I caught them all, or I could do a global search and replace and hope that I didn't catch something that wasn't, that was just literally the string A3 but not used in this context, right? All of that is kind of messy and a pain in the butt and blah, 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 blah. So instead what we do is we define a string, and that's what the pound define is doing. And we're saying the string RTC VCC. That is an arbitrary string that I have given to this, and every time the compiler sees RTC VCC, I want to put A3 in its place.
Right.
It is literally a string substitution. And it happens at compile time, not at runtime.
Right.
Okay?
And so what this means is that if I were to, say, move this over to a Leonardo, and the Leonardo has different pins, rather than having to redefine, again, all the different pins in the code, I just go up here. I say, no. Just change RTC VCC to A6. And boom, I'm done.
Yeah, so there's no A6.
Yeah.
Okay.
That's why I used it. I don't want them to accidentally put that in.
So yes, you can just change the pin definition in one place and recompile, and it propagates all through the rest of the code.
Right.
So we have to find the pins that we're going to be using here. Then you remember from our last week's episode, we talked about the setup function.
There's two things that we need in every single sketch, and that is the setup and the loop.
And the loop. There's the loop. So center. There we go. Setup. So what are we going to do? Well, we want to apply power to the real-time clock. And so I've defined which pins are the VCC and the ground, and I'm going to make them output pins. And then I'm going to digital write a high to the VCC pin, which will output a high voltage, either 3, or 5, I can't remember on this one. And then I'm going to write a low to the ground pin. And so now I've just created 2 power pins. As long as whatever you're powering draws less current than what the Arduino is capable of sourcing, which in this case it is, because this thing pulls like a milliwatt or milliamp or whatever, and the Arduino can do, I think, 20 or 30 milliamps per pin, then this is a way of cheating. And this saved me from having to put the real-time clock on the breadboard and then run a bunch of wires to it.
Right.
Okay? It's just kind of a cheat that I did.
Straight in.
But it works. So we have powered the RTC in those 4 lines. Then the next thing we want to do is we want to set up the serial console for debugging output so that we can see what's going on in my code. The actual final product isn't going to use this, but it's helpful for our development process while we're writing the code and figuring out what it's doing.
It gives you visibility into what's actually happening.
Exactly. So we're going to set up the serial port at that baud rate, 115/200, and then we're going to wait for the serial port to initialize. And then once the serial port is initialized, we will delay by 1/5 of a second just because we're going to print out hello world, which is just a way of letting you know that we've got connectivity, things are working, we have booted up, we're ready to go.
Okay.
Okay. Then the loop. Again, remember from last week that loop just gets called over and over and over again. And so we need to do whatever we're going to do in this time. So TM elements is a data type that is defined in time.h. And what this is an object that has a bunch of different time elements. So you'll see like time.hour, time.minute, time.second. So if you load a time into the TM variable, and we're doing that with the RTC read here, then we can use that to get out all of the internal elements of that time. So it's a grouping of data that all serves the same purpose that we're going to try and get and pull different bits and pieces out of it.
Okay.
So let's go back to the code. So RTC, remember when I told you about we have a library that we use for reading things? That is right there. This line is how we read something from the real-time clock. That is a heck of a lot easier than writing I2C protocol code, right? Somebody else did all the complexity for me. All I have to do is RTC.read, give it a time elements object, and it will populate that time elements object with the current value from the RTC.
Fantastic.
Okay, super easy. So now, after this point, the TM has all of the current time in it. Now you'll notice that we have that wrapped in an if statement. The RTC.read function returns either a true or a false, depending on whether it was able to successfully get a value from the RTC. And we'll look at what happens there a little bit later. For right now, let's assume that it returned a true, which means, yep, I got data. Here's your data in the TM value. What do? Well, right now, we're just trying to make it simple, make sure we can read from the thing, so we print it to the serial port. We print out the hour, a colon, minute, colon, second. Now, you'll notice that I'm not putting any leading zeros in here because I'm trying to keep the code simple.
Exactly.
So it's not going to look like a perfect clock on the serial port, but it's close enough. All right? And that's it. And then when we get to the end of the loop, it goes around and does the same thing.
Right. Now, the nice thing about this is the if statement, the if else, that is our error checking.
That is our error checking.
If the clock has initialized properly, and if it is powered up properly, and if it is giving us data, it will get that nice little unit from the RTC, which we can then strip down and display just what we want.
Correct.
But then the else statement says, if I don't hear from the clock, display this error message.
Exactly.
And Ryan, go ahead and go back.
Go back.
So if we were to pull the clock,
if we get a false from the RTC, the RTC.read says, there was a problem, warning Will Robinson, something happened, then we need to go figure out exactly what that problem is. And so the else for there, and then we do another if.
Right.
If RTC.chip present, which is another function of the RTC object, says, all right, I was able to detect a chip.
But it's not giving me anything.
But it's not giving me the data I want. So if it says, if the chip is present, then print out this error message, which is RTC is present, but I got an error reading from it.
And that last one is I don't see.
I got nothing.
At all.
I got
There's
nothing.
Nothing here.
It ain't there. And then so once
and then I delay a second.
And then we delay 1 second, and that's the bottom of loop.
Nice.
And it just goes back and does it over
simple.
and over again.
And well, we've seen this several times, especially on C#, where yeah, ultimately, your loop should be as short as possible.
Yeah.
If you're doing it the right way, it's not going to be pages and pages because you're just pulling from libraries and saying, okay, I want this function, I want this structure, I want this data, I'm done.
Yeah.
All right, now show us how I would take that sketch and push it up.
Push it up. Okay. So on the Arduino, there is that button which is verify, which just basically means compile the code and make sure it compiles.
Right.
All right. So let's do that. And it just goes through and it compiled the code. Done. All right. That was easy. It didn't print out any error messages.
And
That's
actually,
kinda nice.
can you go ahead and add an error? Let's go show them what the debug
happens?
screen looks like when it doesn't compile properly.
There we go. So let's go up and verify.
There you go.
Error compiling.
So
go ahead and leave it zoomed out because this down here is what we wanted to see. So whenever you see the orange bar there, it says error compiling, and then foo was not declared in the scope. Well, that's true. I
Right,
did not
'cause we just-
declare
yeah.
foo.
It has no idea what you're talking about, and it doesn't want to upload that because that's bad code.
Exactly. So let's remove our foo. There we go. And we will go ahead and verify. There are also keyboard shortcuts for this. Control R for verify.
Right.
R for verify.
And Control U for
upload. Exactly. So we verified our code. Our code works. Let's go ahead and upload it. And that's what that arrow there does. Upload using programmer. Before we get here, oh, that's neat. You need to tell the Arduino IDE what board you're using. We are using an Arduino Uno here. Because the hardware is a little bit different, it needs to know how to compile it for each of the different Arduinos. So we need to tell it it's an Arduino Uno. And then you need to tell it on what serial port it is. It's a USB, but it looks like a serial port. So you'll notice over here that it found the Arduino Uno on dev TTY ACM0. All right, so we select that. Now we're ready to program it. Okay, so let's go ahead and do that. It will build it again, and then now it is currently uploading over the serial port, and it says done uploading. All right, so our program reads from the RTC and outputs to the serial port.
Right.
So now we need to hook up to the serial port and see if we see anything. Luckily, Arduino helps us with that as well. Go to Tools and Serial Monitor. All right, let's bring up the serial monitor. Hey, look at that.
And this is just the information that is pushing back over the serial bus.
That's correct.
So hello world, that was in our that was in the initial statement. That's the system. That's
setup.
The setup. That's the setup. And then right below it, we're now seeing the output from the loop.
Correct.
Fantastic.
That's it.
And that's it. So this has allowed us to take input from the RTC using the library, get the right data, and then push out just the pieces that we want. So that's not actually outputting everything that's coming out of the RCT. It's not just a
Correct.
dump.
Correct.
It's selecting hours, minutes, and seconds. Okay.
That's right.
Now this is very cool. This is decent, but we're not going to leave it here, right? I mean, we do want to go one step further. We are running out of time for this module, but if you want to go ahead and show some of the components you're going to drop on this board.
Absolutely. So right here is a tiny switch, a little push button. We are going to be using push buttons because every clock you need to be able to set the clock, right? The RTC doesn't come necessarily programmed for your time zone or anything else. So
Right.
you need to be able to set it. We're going to use push buttons to be able to do that. Similarly, in the next module, we are going to be outputting analog voltages. And analog voltages often need to be calibrated. And so we have these variable resistors. It's called a potentiometer. This one happens to be a 25-turn variable, a potentiometer. And so you turn that little brass screw head at the top there, and you can set a value between 0 and 10K ohms very precisely. And then we will use that to calibrate our meters so that they output the right thing.
If you followed our links, you've got all these components ready to go. If not, you still have a chance. We're going to put the links again in this week's show notes. If you just saw this project and you said, oh yeah, I want to do that. And hopefully you have, because you've realized this is not magic. There's some people who just get completely discouraged when they first get one of these units because they realize I don't know how to make this do anything.
Yeah.
Smitty just gave you a very easy program to make, something that you should be able to do on your own, and then when we get to next week and we start pushing this out to other devices, you can expand your skill set. Smitty, if you could give them a quick tease of what they're going to see next week, just so that they can wet their beaks, what are they gonna do?
Well, next week I think we're gonna. It depends on how long it takes, but we have some buttons. We're going to be able to set the time on the clock. And if we have time, we might actually hook up some analog panel meters to these things and make it look like a clock.
Fantastic. That's Mark Smith, Smitty, again from DEF CON. You know, I didn't ask you last time, where can people find you if they want to see some of the work that you create?
I spend most of my time on Twitter. I don't use Facebook. I'm on Google+, but I don't really use it. So Twitter is probably the best place for me. At Smitty Halibut, SmittyHalibut. Smitty,
thanks for being our code warrior. We will see you again next week when we take this to the next limit, next level, next
something that starts with an L.
Yeah. Back to you, Padre. Once again, we thank Mark Smith for dropping the knowledge about embedded processors. Now, next week, we're going to get more into the nitty-gritty. We actually kind of ran out of time. You may have noticed that we were really enjoying ourselves. But before we're done, in 2 more episodes, we will show you all the steps you need to be able to build your own analog clock out of an Arduino. Now, I should note that starting next week, we're also going to be having segments on know-how. So make sure you watch know-how, because we're going to show you how to desolder some of the meters, and we're actually going to take you through the step-by-step on the hardware. So you'll get more of the programming on Coding 101, but you're going to get the hardware knowledge on know-how. Make sure that you get that cross team-up thingy going on, because that's where it's going to happen. Let's jump back over to Lou. Lou, you know, one of the things I really like about playing with embedded processors is it gets me back to just being able to feel things. I like to see what I've created. It's great finishing a program and having it do what I expected it to do, but there's something else about being able to actually assemble little bits and pieces.
Yeah, I love that. I do that daily with my son, and it's just it's a great experience to be able to kind of put the stuff together and just see what it comes out to, and seeing his face light up when it moves. It's just amazing.
Right. One of the topics that Smitty touched on was the shields for Arduino, and I got to say, since he played with that hardware in the back, and actually he left some in here in the studio for us, I have been looking through all the shields that are available, and it's amazing. You know, one of the projects that I played with was getting a GSM shield. So that's basically a cell phone shield that you could drop on top of an Arduino. I used the Arduino to be able to control my quadcopter, and then I also had the ability to contact my my Arduino through a cell phone signal. So yeah, the options really get unlimited once you start stacking those things together. Now, one thing I would suggest is you don't stack so many Arduino shields that you get like an Arduino sandwich that it really doesn't work well. You start running over your amperage. Have you had much luck playing with embedded hardware and software?
Yeah, in fact, we attempted to build a alarm system, actually, like what you were saying, with the GSM module that allowed us to, you know, if there was an alarm that went off, we could actually make a phone call or send a piece of data, SMS or whatnot. So we actually tried that out. Problem is, I had some battery problems, so we're still working on it. But that was one of our demo units that we play with.
Yeah, and we said this during the segment, but I think it's worth repeating, which is we know that you could go out and buy something that would probably do what you want it to do for less than it's going to cost you for an Arduino. Because remember, it's not just about the hardware, it's about your time. And most of us, our time gets kind of valuable. But again, it is a great way for you to get back to the foundations of programming, the foundations of knowledge. This is something that we talked about when we were speaking with Steve Gibson. If people actually understand how things work, then they can fix them when they break. Otherwise, it's just a throwaway society. It's, oh, that doesn't work, well, we'll buy the next version. Yeah, that's how it works. Lou, again, we're going to be coming back next week with more embedded programming knowledge, but could you please tell the folks where they can find you between now and then? Because you are getting far more involved with the TWiT TV network. I think the TWiT army needs to start following Lou Maresca.
Yeah, it's appreciated. I love having to be on this show. It's awesome. You can find me at LouMM, L-O-U-M-M on Twitter, about me as well. And of course, check out soon, I'm going to have a new site, it's louism.com. And of course, all my daily work, my daily job, you can find me at crm.dynamics.com.
Ladies and gentlemen, he's Lou Maresca. He's no longer our code warrior. He's our super special co-host. Gotta love that. I like being able to say that again. We know that this was a lot of information. In fact, too much for you to digest in just a couple of minutes that you've had. But we will be giving you full notes. That includes the parts list once again, including where you could check out some of those shields that Lou and I were talking about, and the code. So if you want to check out the code that Smitty was playing with, we will give it to you. It will be available on our show notes page which you'll find at twit.tv/code or coding101 or code 101. It all goes to the same place. This is important because not only will you get our show notes, but you'll also get the entire backlog of episodes. So if you want to go back and download the first Smitty episode so you don't miss a thing, or if you want to listen to us talk about to Steve Gibson about the foundations of programming for 3 episodes, you can do that. Or if you want to go back to the very beginning and listen to Lou Maresca talk about C#, you can do that. Just drop by our show notes page and it's right there. Also, don't forget that we do this show kind of live. We're doing it live right now, every Thursday at 1:30 p.m. Pacific time. That's going to be changing in March. We're going to be moving to a pre-recorded format because we want to be able to get in more hosts, more guests, more people who can will show us some of the cool things that they're working on, which means you need to watch the calendar for when we're actually going to be live, because Mondays will mostly be the pre-record day. But if you happen to drop in on the live recording, make sure to go into our chat room at irc.twit.tv. It's a great place for you to find out what we're doing and for me to read questions from you as the show is going on. Lastly, I want to thank everyone who makes this show possible, to Lisa, to Leo, to Cranky Hippo, my usual TD, but today to Zach, because Zach has been my TD for the last 2 weeks, and he is awesome. Zach, could you please tell the folks where they can find you? Because I believe you're in a follower war with Jeff Needles, and we need to make sure that you have more followers than he.
Yes, that's correct. You can find me on Twitter at Eskimo Zach, and followers are appreciated.
Right, and actually we're running a contest. If you follow Zach, go back to you, Zach, because they need your follow Zach at Eskimo Zach. Follow him, and one of his followers may win a brand new Arduino. May. I mean, I don't know where it's going to come from. It's not from us, but follow him anyways because he's a good guy. Thanks, Zach. Until next time, he's Lou Maresca. I'm Father Robert Balacer. End of line.